Our solar system began as an immense swirling cloud of dust and gas. Imagine a vast, dark nebula, a cosmic nursery filled with the remnants of ancient stars. This nebula, composed primarily of hydrogen and helium, held the seeds of what would become our sun, planets, and moons. Over time, gravity began to draw these particles together. As gravity pulled the dust and gas inwards, the nebula began to shrink and spin. This rotation caused the nebula to flatten into a rotating disk, resembling a giant cosmic frisbee. At the center of this disk, the density and temperature began to rise dramatically. This central region, destined to become our sun, was the heart of the nascent solar system. Our solar system, born from this cosmic dance of dust and gas, is a testament to the power of gravity. At the heart of the swirling disk, gravity continued to pull matter inwards, compressing the gas and dust to incredible densities. The temperature at the center soared to millions of degrees, hot enough to ignite nuclear fusion, the process that powers stars. Hydrogen atoms began to fuse together, forming helium and releasing vast amounts of energy. This marked the birth of our sun, a blazing inferno of nuclear fire. The intense radiation and solar wind swept through the surrounding disk, pushing lighter elements like hydrogen and helium outwards. The inner regions of the disk, closer to the sun's intense heat, were left with mostly heavier elements, like iron and silicon. These elements condensed into solid grains, forming the building blocks of the terrestrial planets, Mercury, Venus, Earth, and Mars. The sun's energy sculpted the solar system, creating the diverse array of planets we observe today. Within the protoplanetary disk, the dust grains began to collide and stick together. These tiny particles gradually coalesced into larger pebbles, then rocks, and eventually planetesimals. As the planetesimals grew larger, their gravitational pull increased, attracting more material. These growing bodies collided with each other, sometimes shattering into fragments but often merging to form even larger objects. Over millions of years, this process led to the formation of protoplanets. The protoplanets continued to accrete material, clearing out their orbits, and eventually becoming the planets we know today. In the inner solar system, the terrestrial planets formed from the rocky remnants of the protoplanetary disk. Further out, the giant planets formed from a mixture of rock, ice, and vast amounts of captured gas. The formation of the solar system was a remarkably rapid event on cosmic timescales. From the initial collapse of the nebula to the formation of the planets, the entire process took only about 100 million years. The first stage, the collapse of the nebula and the formation of the protoplanetary disk, occurred within a few million years. The ignition of the sun followed shortly thereafter. The accretion of planetesimals and the formation of protoplanets took tens of millions of years. By about 4.5 billion years ago, the solar system had largely taken its current form. Jupiter, the largest planet, likely formed slightly earlier than the other planets, accumulating a significant amount of mass within the first few million years. Determining the age of planets is a challenging task, but scientists have developed ingenious methods to unravel the deep history of our solar system. The primary method relies on radiometric dating, a technique that measures the decay of radioactive isotopes within rocks and minerals. By measuring the ratio of parent isotopes to daughter isotopes in a sample, scientists can determine how much time has elapsed since the rock or mineral solidified. This provides a precise age for the sample, allowing us to date the formation of planets and other celestial bodies. The age of the solar system is estimated to be around 4.5 billion years, based on radiometric dating of meteorites. Meteorites are believed to be remnants of the early solar system, providing a valuable window into the conditions that prevailed during planetary formation. Meteorites, fragments of rock and metal that survive their fiery plunge through Earth's atmosphere, are invaluable time capsules from the early solar system. These cosmic messengers provide critical clues about the conditions that prevailed during the solar system's formation. One of the most significant meteorites ever discovered is Erg-Chech 002, a volcanic rock found in the Erg-Chech Dune Sea in Algeria. This remarkable meteorite, dated to be 4.566 billion years old, is the oldest known igneous rock, providing a direct glimpse into the early stages of planetary formation. Erg-Chech 002's composition suggests that it originated from a differentiated protoplanet, a body that had begun to separate into layers like Earth's core and mantle. The study of meteorites like Erdchech 002 continues to provide valuable insights into the formation and evolution of the solar system.